So, good morning to all of you in this new lecture. So, what we will do is that first we will review the last lecture in which we discussed basically mechanisms of polarization. So, first of these mechanism is atomic or what we call as electronic polarization. This is basically separation of charges at the very small level, that is at the level of atom. And what happens is you have shifting of centers of positive negative charges, that is shifting of electron cloud with respect to the nucleus, and this typically happens at the frequencies, optical frequencies, very high frequencies. And in such a situation this can also be explained by Maxwell's equation, and as a result epsilon r in this range happens to be equal to n square. Then you have ionic polarization, which is separation of ions. Now, this happens in solids which are ionic solids, which have anions and cations. So, as a result you have shifting of positive and negative ions with respect to each other, and this happens at slightly lower frequencies because of higher mass of entities involved, and as a result time taken is larger, and hence the frequencies are in the range of 10 to the 9 to 12 hertz. And one example which we took was in ACL, and third one was a dipolar polarization, which involves movement of dipoles. Now, this happens in solids which have first of all permanent dipole moments. So, just for example the materials like water, etc., materials like water and any other polarizable solid which has a permanent dipole moment. So, water molecule would be something like that. So, this is, let us say, hydrogen, and this is oxygen. So, as a result you have a permanent dipole moment irrespective of applied field. Now, what happens is when in such a solid it is the alignment of this dipolar vector along the direction of applied field, and this gives rise to, so for example, if the field was in this direction, then this whole thing has to rotate in this direction. So, as a result here you have rotation of dipoles, which can happen in the frequency range anywhere between below 10 to the 9 hertz. So, because this involves rotation of higher masses, as a result larger times are required. And then you have interface polarization, which happens because of defects such as grain boundaries, porosity, or contact interfaces, etc. So, one situation can be you have electrodes, and as a result you have polarization at the electrode interface, or you can have porosities or any discontinuities in the sample, and they also give rise to charge buildup at the interfaces, and this is because of interface. This is called an interface polarization. Typically happens at very low frequencies, although in some systems you can observe at about 100 hertz as well, but typically it happens below 1 hertz. So, the total dielectric constant happens to be equal to sum of electronic contribution plus ionic contribution plus dipolar contribution plus interfacial contribution. Okay. Typically, now what we will do is that we will, as I said, we will take mathematical treatment of these first three, but interface we will not take into this course. What I will do is that I will provide you some references where you can go through. It is a little tedious, and but it can be modeled using other methods which I will talk about later in the course. So, this is how the plot looks like. You have interface. So, you start from high frequencies, you have electronic contribution followed by ionic contribution followed by dipolar contribution followed by now the interfacial contribution. Okay. So, this could be anything, sum of all these is the total dielectric constant. Then we looked at certain values of various systems. Finally, what we did was we took a microscopic approach, and we worked for a system having n dipole moments per unit volume, and from that what we determined was a quantity called as polarizability. And this polarizability is a microscopic quantity, it is an atomic property or local property rather, and this is given as alpha I, and this is equal to your dipole moment divided by the local field. So, mu is equal to alpha E. So, mu is dipole moment is related to electric field by a microscopic quantity alpha, and this again this alpha is also alpha, which could be sum of various alphas. So, you can have electronic, you can have ionic, you can have dipolar, as well as you can have interface. What we will do is that now we will establish formalisms for each of these alphas except interfacial alpha. Before we do that, however, we would look at the origin of what is called as local field, because what happens in reality is that we apply a field E, but the field experienced which is locally by the solid or the atoms inside the solid is rather different. It happens to be different because of presence of surrounding medium which modify this applied field. As a result, the local field is slightly different, and that is what we are going to do now. So, this is lecture number 18. So, this local field, so we define it as E loc, and this could be due to polarization effects in the surrounding media. Okay. It could be either around a dipole or a molecule or whatever, basically the entities which make up this dielectric. So, what happens that since on a macroscopic scale the material is electrically neutral, so what you would expect is the overall field in the material to be equal to 0, but when we start looking at individual dipoles and molecules, we find that this is not the case, and this local field is basically nothing but sum of applied field with lot of other fields, and this you can in principle solve using Poisson's equation, which basically couples charge density and the applied field. But if you start doing it from Poisson's equations, it becomes very complicated and cumbersome. So, another model which is simpler model is called as Lorentz model. So, basically this problem of local field can be solved using Poisson's equation or Lorentz model, and we will take the second one, which is a simpler approach and which gives reasonably good agreement with what is observed. So, what we will do is that we will take a model dielectric. So, let us say this is our dielectric material, okay, and this dielectric material, let us say we take out a group of atoms away from the material. So, let us say we take this volume of material, a sphere, we create a spherical cavity. So, let us say this is the material. So, we have taken this out, and the material could remain, it could have some structure inside it. So, basically you can have atoms sitting here. So, a group of atoms is taken out in the form here. So, this gives rise to, now when you take out this sphere away from the material, this gives rise to creation of charges on the surface. So, you have positive charges, let us say on this side depending upon the direction of applied field, and negative here, and so you have applied field in this direction. This is E applied, okay. So, this E applied, you would have typically the plates this side. So, plates would be positively polarized, charged, these would be negatively charged. So, your E app is in this direction, consequently you will have surface charges minus 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 here on the surface of dielectric and plus on the left side. So, as a result you have applied field in this direction, you have a creation of another field which is called as ED, which is the depolarizing field, and this is due to build up of surface charges. And when you take a cavity, when you take a volume of material out, create a cavity inside, then the surface charges on the surface of the cavity would be opposite to the what you see on the surface of the material. So, as a result you have applied field which is in this direction minus x in this case. To oppose that, you have now this applied field causes polarization in the material. To oppose this polarization, you have an inbuilt field which is called as depolarizing field, which is in the opposite direction. Now what about this cavity? This cavity produces field which is called as Lorentz field, and the direction of this Lorentz field would be equal to EL in the direction of applied field. So this would give rise to what is called as EL, Lorentz field. And another field which is there is at the center of this material, which is called as E center, because of presence of surrounding atoms. So basically you have these 4 different kinds of fields, and all these 4 different kinds of fields are not at the same scale. There are some fields which are macroscopic in nature, there are some fields which are microscopic in nature, and you can see which of these are microscopic and microscopic. So macroscopic fields are of course one is the E applied, which is the microscopic, and then second is the depolarizing field, which is the ED. These two are the macroscopic field, and your E center as well as Lorentz field, both of these are microscopic fields. Considering dielectric as a continuum, this approach is built up. So this total field, so this E local now is nothing but sum of all these fields. So we have E app, okay, minus ED, depolarizing field, plus E Lorentz plus E center. Now for, let us say, for isotropic material, now this was shown by Lorentz himself, that for isotropic material, and most of the polycrystalline material can be considered as isotropic, this E center can be taken as 0. So this cancels out. So what you have now is, you are now left with EL and E app minus ED. So the question is how to work out these two. This is what we will do now. Now we know that E applies minus ED, which is the macroscopic field, which is basically equal to nothing but the field which is experienced macroscopically by the dielectric or capacitor. This is equal to something called as E naught, and this is what we experience when we apply a potential to the dielectric, and this E naught is nothing but E minus P divided by epsilon naught, assuming epsilon r was equal to 1, and this E is nothing but V by D. Okay. So basically what we have done is this E app, or rather we can, let's not make it very confusing, let's just make it E app minus ED was equal to E minus P divided by epsilon naught, where P is nothing but the P by epsilon naught is the depolarizing field. This comes from your Maxwell equations. Now another field which is left now is EL. So how to work out the EL? For this we take the shape of the spherical cavity. This is the spherical cavity, and now if you go to previous picture, so we are looking at this way, which means the positive charges are up, negative charges are down. So looking at the direction of EL. So for this you have let us say this is the center. So what you have here is, if I So, this is the spherical cavity which has charges around it, and each of the so now this you can divide this spherical cavity into smaller areas. So, let us choose a segment dA here for example. So, this would be something like this. Oops. Okay. Making the angle theta of the thickness, angular thickness d theta. Similarly, here theta and d theta. Okay. And let us say the radius of this sphere is r. So, if this is the element dA, small dA, both of them, okay, then the normal component of polarization of this small element which gives rise to what is called as surface charge density, because polarization as we know is surface charge density. So, the polarization is in this direction because the material is polarized along this direction, and this is, let us say, is the normal vector normal to the area dA, and since you have dAs all over the place, you will have normals varying over all the different direction. So, as a result, polarization makes an angle theta with respect to, so this angle would also be theta. So, polarization makes an angle theta to the surface normal of area dA, and each of these gives rise to a field which is DEL. Okay. And what you get here now is 2 DEL cos theta. This is the only field which survives, the other components cancel each other, as you can see from the symmetry, because for each segment on the upper half of this sphere, you have another segment at the bottom half. Now, the only thing that you have to be careful about is the sign. So, what happens is that when you take for this for a segment on this side will have polarization on this side, as a result you have a component in this direction, component in that direction, and what happens is that these two components, the horizontal components, cancel each other because the sign is now negative, and as a result you have only the vertical components surviving. So, what happens is, now you can write this normal component of polarization so P dot n dA, this is equal to P cos theta dA, all right. What you can do is that in order to find out dE2, you can invoke what is called as Coulomb's law. So, if you apply Coulomb's law, from which you can calculate field and apply Coulomb's law, and then you get radial field intensity, which is given as dE2, and this is equal to P cos theta dA. P cos theta dA would be the charge, okay, and you know that Coulomb's law is F is equal to Q1 Q2 divided by 4 pi epsilon naught r square, and if you want to calculate E, then you take one of the charges on the other side. So, that gives you electric field, because F by E is the electric field, and then you get Q divided by 4 pi epsilon naught r square. So, this is your charge, and r is the separation distance, which is, as you can see from the sphere. So, if Now, for as we said that for each dA in the upper half, you have another dA in the negative in the lower half, but due to the change in the polarity of charges, what happens to the horizontal components cancel each other, the vertical components survive. So, the total field component is 2 EL 2 DEL cos theta, these survive. So, E2, so this EL can be, so overall EL can be calculated for a sphere DEL cos theta, and this is equal to, if you replace the magnitude for DL, then this becomes P cos square theta dA divided by 4 pi epsilon naught r square. Okay. Now, dA, how can you calculate dA? If you have this sphere like this, the radius is r and we are looking at this small segment of thickness d theta, and we know that this segment goes like this. So, the area of this segment would be r sin theta into, because you have the angle theta here. So, this would be r sin theta because this is r. Okay. So, this is r sin theta and this would be, the another side would be r d theta. So, this dA would be equal to r square sin theta d theta. So, if you expand dA, it would look like this, right, sorry, 2 pi r d theta. So, r sin theta into 2 pi r d theta, and this would give us 2 pi r square. So, this would be basically, what it would be is like this, 2 r sin theta So, if I modify this as 2r sin theta into r d theta. Okay. Now, you replace dA in the previous equation. So, your EL becomes equal to, now you integrate from 0 to pi, because upper half is symmetric, because you are taking from theta from this. So, theta goes from here to here. So, that is 0 to pi. Okay. So, this becomes 0 to pi p cos square theta into 2 pi r square sin theta d theta divided by 4 pi epsilon naught r square. So, this becomes a manageable equation, you can solve it easily, and this gives rise to what is solution is 1 by 3 p divided by epsilon naught. So, this Lorentz field EL is p divided by 3 epsilon naught. So, this is a Lorentz field that we have got. So, what we have got is, we have got hang of most of the fields, and so the local field now is E local is now E applied minus ED plus P divided by 3 epsilon naught, and we have said that this E applied minus ED is what is felt by the capacitor. So, let us say this is equal to something called as E naught plus P divided by 3 epsilon naught, and we know that P is equal to epsilon naught epsilon r minus 1 into E naught, what is felt by the, this is a macroscopic equation, right. So, we can plug that back in here, and as a result we get E local equal to E naught plus epsilon naught epsilon r minus 1 E naught divided by 3 epsilon naught. So, these cancel each other, and what you get is, so if you just rework this equation, what you get is E naught divided by 3 into epsilon r plus, so plus 2. So, you got this expression for E local in terms of the field which is experienced by the dielectric macroscopically. Okay. So, you can see that the macroscopic field which is experienced by the dielectric is different from the local field. So, or the local field is different from the macroscopic field which is measured due to application of applied voltage. Now, if you combine now this, so you got E local is equal to E naught divided by 3 into epsilon r plus 2, and we know that P in terms of polarizability is N I alpha I into E local from the previous lecture. Okay. So, here we are relating polarization to polarizability and the local field. Okay. This is what we established in the last lecture. So, this would be equal to N I alpha I E naught by 3 epsilon r plus 2. Now, again we put the expression for P. So, this is the expression for P in the microscopic quantities. What is the expression for P in the macroscopic quantities? P is also equal to epsilon naught epsilon r minus 1 E naught. Okay. So, if we equate these two equations top and bottom, so what we get is epsilon r epsilon naught epsilon r minus 1 E naught is equal to N I alpha I E naught by 3 into epsilon r plus 2. Okay. So, what will happen now is E naught will cancel each other, and if you just work them around, work this all the parameters around. So, the objective is to bring the microscopic parameters on one side, macroscopic on the other side. So, what is the microscopic parameter? Alpha is a microscopic parameter, epsilon naught is microscopic parameter, while it is a fundamental quantity, n is the microscopic parameter. What is the macroscopic parameter? Macroscopic means something which you can measure macroscopically, and this is epsilon r. So, when you take all these, when you rearrange the parameters, what you get is N I alpha I divided by 3 epsilon naught is equal to epsilon r minus 1 divided by epsilon r plus 2. And this equation is a very useful, very famous equation, which is called as Clausius-Mosotty relation. And what this equation does is, this equation relates the microscopic parameters for a dielectric material to the macroscopic parameters by taking use of a modified field which is called as a local field, which is experienced locally by the dielectric rather than the overall field which is experienced by the dielectric. So, what it does is, if you know epsilon r from the measurements, you can measure, you can calculate alpha I for a given system, given the fact that you would know what is N I for a system. So, now this alpha I, as I said before, is again sigma alpha. So, this is net polarizability alpha would be sum of electronic, ionic and dipolar, as we have looked before. You can apply as a special case this equation to the gases. So, for gases, this epsilon r minus 1 is much smaller than 1. So, what will happen in such a case? If it is much smaller than 1, so and at lower pressures it becomes epsilon r plus 2 will become approximately equal to 3, and as a result n alpha divided by epsilon naught will become epsilon r minus 1, and that is equal to chi. So, this is equal to what we got earlier. So, for gases this equation modifies to the previous form that we got. Okay. So, what now we will do is that, so we will just summarize this part before we move on to the next part. So, what we have done is, we have studied the various mechanisms of polarization, and from that that point onward we looked at a microscopic quantity which is called as alpha, which is the polarizability. Now, this polarizability is something which you cannot measure directly. So, as a result you need parameters to measure it, and those parameters are macroscopic parameters. We also introduced a concept of local field, which is the field which is locally experienced by the dielectric material when the field is applied. So, you have an external field which is due to the external voltage which is applied to the system. So, as a result this external field, but this external field is different and local field is different. And why this local field is there? Because the external field causes the polarization. Now, polarization, so when you measure the field at a particular point, not only you have polarization because of applied field, but also because of the surrounding media which is present around this particular piece of particular point in the material. So, then you then we establish various different kinds of fields. So, you have applied field, you have what is called as depolarizing fields. So, applied field, depolarizing field put together make what is called as E naught, which is the macroscopic field which is experienced because of application of voltage. And then you have what is called as a Lorentz field, which is the internal field because of charge buildup on the surface of this sphere which you took out. So, assuming that it was taken. So, on each sphere at every place in the material you will have a Lorentz field. So, we then worked out what is the Lorentz field, and then E center, which is a center which is the field at the center of the material, that was taken as equal to 0 because of assuming that materials are isotropic. And then we calculated what is called as local field, which is different from the applied field, and this E local is helpful in then relating the microscopic parameters to the macroscopic parameters. So, we have seen how the polarization takes place, and we have also introduced the concept of local field and tried to relate microscopic and macroscopic parameters for a dielectric material. Now, what we will do is that we will calculate this alpha, which is the polarizability, for each of the mechanism that we talked about. So, what we will do is that we will first calculate. So, let us determination of okay. So, first we will take the case of electronic polarization, and this is the simplest. Now, in case of electronic polarization, assume the atom to be a perfect sphere. So, this is the center of atom, this is the nucleus, and around it what you have is this does not look like a perfect sphere. I will have to draw it again better. So, you have a nucleus, you have the surrounding electron cloud. So, nucleus of charge plus Ze and electron cloud will have minus Ze. Okay. So, in the absence of electric field, the center of this electron cloud matches with the center of nucleus. So, as a result, in that when E is equal to 0, mu is equal to 0. Okay. Now, what happens when you apply the field? When you apply the field, the center of this positive charge moves with respect to center of negative charge. So, so let us say upon application of field. So, bad. So, we have, so this is the center. So, let us say this is negative, okay, and the positive is somewhere here. So, this is your center of positive charge. So, if I just draw another circle, So, these two guys have moved by a distance d. Okay. So, this would be minus q, this would be plus q, and we know that q is equal to z e, right, and let us say this whole thing is equal to 2r, and we apply the field in, this is applied field. Okay. So, so when you apply the field E, then the force which is created on the system, so force F1 which is due to application of electric field can be given as, so F1 can be given as ZE E. Let us say this is equation number 1. Okay. So, now if you have force one which is first force is because of creation of applied field which separates the center of positive charge and they move by a distance d. So, when they move by a distance d, you have a Coulombic attraction force, and this Coulombic attraction force because of opposite charges. So, this Coulombic force F2 is given as, F2 is given as q of nucleus multiplied by q of electrons within this sphere of radius d, q in sphere of radius d, or q in the distance d, and this would be divided by 4 pi epsilon naught into d square. Okay. So, this F2 can be written as ZE multiplied by again ZE, and this would be 4 by 3 pi d cube divided by 4 by 3 pi capital R cube. So, within that distance d, the number of electrons enclosed. So, this F2 can be written as, so first was q of nucleus ZE multiplied by the charge, the electrons inside the distance d, electronic charge inside the distance d. So, that would be ZE into 4 by 3 d cube, the volume of the radius of d, volume of the sphere of radius d divided by the volume of the whole electronic sphere, and this will be divided by 4 pi epsilon naught d square. So, this would be further simplified as z square E square, you have 1 d left because 2 d's cancel each other, divided by 4 pi epsilon naught r cube. Now, at equilibrium, F1 will be equal to F2, and let us say d is equal to at equilibrium distance, which is called as d naught. So, when you do that, so ZE E is equal to z square E square d divided by 4 pi epsilon naught r cube. So, these one of the ZE's cancel here, d will be d naught, and this gives rise to, if you work it out, this will be d naught to be equal to 4 pi epsilon naught r cube E divided by Z E. So, this will be the equilibrium separation distance. So, the induced dipole moment, would be mu, which would be equal to Z E d naught. So, this would be Z. So, Z e dot 4 pi epsilon naught r cube E divided by Z e, Z e cancel each other. So, what you get is 4 pi epsilon naught r cube E, and you know that mu is equal to alpha E. So, this is alpha electronic. So, what it gives you is that, so alpha electronic becomes 4 pi epsilon naught r cube, and the, if let us say if n was the dipole density, number of dipoles per unit volume, then polarization becomes n into 4 pi epsilon naught r cube into E. So, this is the polarization that you get. So, what this equation tells you, the implications of this equation are pretty important. The implications of this equation are that larger the atom is, more the polarizability of the material is, which means more the material can be polarized. So, this is the first conclusion. Secondly, from this you can also find out what is the susceptibility. So, susceptibility, electronic susceptibility would be 4 pi n capital R cube, because P is equal to, you can equate it to chi epsilon naught E. Okay. So, this gives rise to what is called as susceptibility. So, basically higher the radius of the atom is, higher the susceptibility and the polarization of the material would be, you have, and this also shows that you have a linear relationship between the polarization and electric field, at least for this particular mechanism, and you can also relate from this the you can also compare the polarizabilities of various types of atoms. For instance, the polarizability of alkali and rare earth, alkali rare earth atoms is, alkali earth atoms is more than the D atoms, because of shielding of electrons, shielding of nucleus by the electrons in D type of materials. So, as a result, S and P type of materials tend to have higher polarizability as compared to D type materials. So, what we will do now is we will just look at some of the values, and another observation is, since R for anions is typically larger than R for cations, anions tend to be more polarizable as compared to cations. So, for some values for a few atoms, so fluorine, so this alpha is into 10 to the power 24 centimeter cube. So, this would be 1.2, chlorine 3, bromine 4.5, and then iodine is 7. So, you can see as the size increases, the polarizability increases. Now, for alkalis, lithium had 0.03, sodium has 0.3, potassium has 0.9. So, again the number goes up, but you can see that cations have much smaller number as compared to anions, and that is because of bigger size of the anions as compared to cations. So, anions in general are more polarizable as compared to cations, and this is more important from the point of view of solids which have mixture of anions and cations. Now, the second mechanism for this we will take is ionic polarizability. Okay. So, in case of ionic polarizability, this happens in ionic solids where you have presence of cations and anions. So, in the absence of electric field, let us again take the case of sodium chloride. So, you have, so these are, let us say, all right, and again you have so these are your chlorine ions. So, there is the 001 phase of sodium chloride, and then your sodium ions will go in the octahedral site and at least on this face on the edge centers. So, now each of this sodium and chlorine ion make a dipole, but the direction of each of these dipole is equal and opposite. As a result, when E is equal to 0, mu is equal to 0. Okay. Now, what happens when you apply electric field? So, as a result of symmetry, when you apply there is no electric field, when there is no electric field, the net dipole moment is equal to 0, because all the components cancel each other. So, when you apply electric field, what happens is, so let us say the picture gets modified a little bit. So, what I will do is that I will keep the anions fixed and move the cations. I will just make this a little bigger in order to be a little bit more clear. So, these are anions. Now, what happens is, if the field is applied in this direction, which is the E, then the cations move to, let us say, this side. Hang on, we forgot to draw another anion here. Okay. So, all these ions will move closer to okay. So, and even here. So, as a result, what has happened is you have two different distances between the positive and negative ions. So, this is, let us say, one distance, this is another distance. So, as a result of unequal separation, you have a net dipole moment created inside the material. So, when E is not equal to 0, mu is greater than 0, it is finite dipole moment. So, this illustration probably explains that much better. So, basically what happens is that you can say that the distance between you can take the distance to be increasing or decreasing, it does not matter, because ultimately it is a question of relative increase. So, let us say this, now whatever the distance is, the distance increases by a certain magnitude on one side and decreases by a certain magnitude on the other side. So, let us say this increase or decrease is defined as, so this change in separation between ions is defined as d. Okay. So, we are interested in calculating the magnitude of this d. So, first when we apply electric field, then the force F1 which increases the decreases the distance between the ions. Let us say the ions have charge q. So, the charge on the ions is q, plus or minus q. So, this F1 would be equal to QE, okay, which is the same force due to electric field. Now, in the ionic systems, if you remember, we earlier introduced that ionic systems, when you have positive and negative charges, then they tend to have a bond between them, and this bond is, let us say this bond is like a spring. So, this spring tends to restore these two ions back to equilibrium position. So, the restoring force the restoring force is given as F2, okay, and this F2 is given as K dot D, let us say K I for a given kind of system, K I, where K is this spring constant which depends upon the bond and D is the distance. Okay. So, so this we have done assuming that the bonds between two ions act like springs. So, again at equilibrium we would like to equate them. F1 becomes equal to F2, and also what is K? So, K is spring constant which is related to a physical quantity, and that is called as modulus of elasticity. So, if Y was the modulus of elasticity and D naught was the separation distance, then this K I becomes equal to Y D naught, and at equilibrium F1 is F2 equal to F2 and D is equal to D naught. So, again we match the two equations. So, that is Q into E was equal to Y D naught into D, sorry. So, this K the spring constant refers to the equilibrium distance. So, what you will have in this expression is Y D naught multiplied by K D, so multiplied by D. So, basically this is K and this is the distance. So, this gives you the magnitude for D, and this becomes Q E divided by Y D naught, and this D is not the equilibrium separation. So, this will not be equilibrium, this is just the magnitude of increase or decrease between the distance. So, this D naught is nothing but related to lattice parameter or equilibrium distance between the ions. So, now from this D you can calculate what is mu. Mu you know is Q D, which is a dipole moment, and this is Q square E divided by Y D naught. So, again this particular term without E becomes alpha ionic or alpha I. So, this, and as a result the polarization becomes, if dipole density was again n per unit volume. So, this will become n mu, and this would be n Q square E divided by Y D naught, and this would be the expression for P. So, again what this equation tells you is that smaller the higher the modulus of elasticity is, the less polarizable the material is, and that makes sense. Higher the modulus of elasticity, which means higher the bond strength. If the bonds are stronger, they are not going to be stretched or compressed that easily. So, as a result the polarization of the material goes down. So, so I will give you some values for this particular. So, for example, zinc oxide 4.6, zinc sulphide 5.1, zinc selenide 5.8, cadmium sulphide 5.2. So, of course, this analysis also does not take care of any covalency. So, we have to take care of that. It is a very rough guide, but it works reasonably well. Cadmium selenide 7. So, basically the here these values are epsilon r values. So, they are increasing. So, they are increasing as you go within the for the zinc you go from oxygen to sulfur to selenium, and what basically it means is that the bond strength is going down. So, as a result the polarization is increasing. So, what we have done is we have covered the origin of local field, and we on the basis of that we have come up with an equation which is called as Clausius-Mosset equation relating the microscopic and macroscopic parameters, and then we did the evaluation of electronic and ionic polarizability, which are dependent upon parameters like, for example, electronic polarizability dependent upon the size of the atom, and ionic polarizability is dependent upon the bond strength. So, in the next class we will take up the dipolar polarizability, which is a little bit more comprehensive in terms of its analysis. Thank you.